Welcome back. So we are going to continue our journey towards the physical level of Spark and ultimately data frames and Spark SQL. So this is where we were. I told you this is fake. This is not how things happen. This is how things happen. There is a condition for this. It's because we only had narrow dependency transformations, no spaghetti in there. That's the reason we can do it. And what we optimize here is that we do not materialize the RDDs in the middle. We only materialize the first one and the last one. The ones in the middle are not materialized, right? So this is the difference. This is new to Spark. This we haven't seen in MapReduce, right? Because in MapReduce, there's no such thing as multiple maps one after the other. It doesn't exist. But you saw that there's a lot of things that are in common with MapReduce, right? Is there a question? We can try with the microphones so people on Zoom hear you. So which one is bringing you the microphone? Awesome, go ahead.
Okay, so for the intermediate RDDs that are not materialized, what happens if they are in turn used for other transformations? So
then you would materialize them.
So you need to materialize them in that case.
If you have another transformation for which there would be the last ones. Imagine, for example, in that case, you had a chain, but imagine that now I take this RDD right here, which I have in my Python notebook as some sort of object with this RDD, and I call collect on it. Then it's going to materialize it, right? It's going to be collected and downloaded, and then it's materialized. Or maybe you would have, right after this RDD, in a different path on your DAG, you might have some join or sort or group or something that has spaghetti in there. Then that would force a materialization of this one, right? So it might be that in some context, you do not need to materialize them in that context, but in a different context, if it's reused in the DAG, right? In a DAG, you might have multiple edges from a node, right? So if there is another edge in the DAG reusing this in a different way, it might be that we need to materialize it, right? Does it make sense?
Yes.
Awesome. All right. There's a name for this. It's called a stage. It's called a stage. A stage is when we group multiple narrow dependency, non-spaghetti transformations into a single round of execution, right? Divided in tasks. So when I have a stage, I can spread it as tasks over multiple machines, but as a single set of tasks without materializing the RDDs in the middle, right? So that's just another way of displaying it now. That's physical, that's logical. I really have, in that case, 4 RDDs with 3 edges in the middle. These 3 edges correspond to narrow dependency, non-spaghetti transformations, and thus I can group them as a stage. All right, so that's a narrow dependency. That's the fancy name for non-spaghetti. And in that case, you can actually stay on the same machines without materializing what's in the middle, same stage. So this is what happens if we use spread a stage over cores, and that stage consists of multiple non-spaghetti transformation. What's very important to understand is the order of execution in here. So in that case, the blue RDD is materialized, the green RDD is materialized, but not the orange one in the middle. This one is not materialized. Let's look at the order of execution. I'm going to take core 1, the slot right here. Remember that cores are unable to do things in parallel. Technically, you can use threads, but you know that threads is only a fake way of getting parallelism, right? You still do it sequentially, you just alternate. But in the case of Spark, you really do one thing at a time on one virtual core. So I take this core. It's going to take this value, call maybe a filter function and a map function, and then keep that in memory. Then it's going to go to the next value, call map, call filter, keep that in memory, and throwing every time this away. Then it takes the next one, calls map, call filter, keeps it in memory, and throw this away. It's done with the task, so this stays in memory. If there is enough space in memory, this stays in memory. Then it moves on to another task, dynamically, getting it from the next ones available, takes the blue value, calls map, calls filter, throws that away, keeps the green one. Takes the next value, the blue one, calls map, calls filter, keeps that. Next value, blue one, orange, keeps that. You see that this is all sequential within the task and across the tasks in the same slot, all sequential. There is absolutely no parallelism in there. The parallelism is when we have these multiple virtual cores that are processing this in parallel. For whom is that clear? All right, super important, but it's not new to you. We saw it in MapReduce. It was the same idea, right? That it's only parallel across the slots, right? Also, I already said it, but I'm repeating it. The number of virtual cores is typically double the number of physical cores on the processor. This is because of hyper-threading. So if you have actually 8 physical cores, you have 16 virtual cores. It's an optimization on the hardware. It's as if you had 16 layers of parallelism. All right. So this now should all make sense to you, right? Executors, shared memory, multiple cores, executing the tasks sequentially and weaving the tasks going top down and then left to right, like a depth first search. Yeah, go ahead. Internally, this is all done. So the question is whether this is done by the user internally. What I'm showing to you is entirely in the Spark code, the Apache Spark code. In fact, from your notebook, you don't see that. In your notebook, you just press a button and wait. You might see some fancy animation of something that rotates or whatever during the time to keep you company. And then you see the final results on your screen. All of that is automagical. It just works. It just happens. Of course, you have ways to tune the parameters, right? There are ways you can set up some variables in a way, in another. You can also give a few hints. For example, if you want to pin an RDD, then you need to do it yourself with the code. But if you don't do anything, it's still going to work, right? The reason you can use pins and so on is that in some cases, you're helping Spark being faster, right? But an ideal system in the future wouldn't need your help, but you know that we don't get there instantly, right? So in the meantime, we just need to help the computer a bit, yes? Yes, exactly, that's the idea. So it's basically a pragmatic view of data independence. That's how I would call it. If we jumped, let's say, to the 22nd century, maybe the computer systems are so evolved and mature that they figure it all for you. And you don't need to worry about it. In fact, you're just talking with ChatGPT and it's just going on like this. But in practice, it's very, very tough to do. And the fact is, it's actually a problem that is undecidable, or that is you will never be done with it, basically. You will keep adding optimizations. There will always be optimizations you didn't think of, right? So there is no way you resolve it all. You might, at some point, tackle 99.99% of the cases. There will still be a few cases you didn't tackle. Today, we are not quite there yet in the current implementation status. And this is why you need to kind of be a bit flexible with data independence in the sense that having some knowledge about how the systems work helps you writing your queries in a way that is more likely to execute fast, right? In the 22nd century, you will no longer need to do that. You can give a very inefficient query, it figures it out. But today, the computers need a little bit of your help for this. So this is why it's still useful. So useful for two goals. That's the goal for the user. Being a bit aware of what's going on helps. And the second reason why I'm teaching you this is that you might be the engineers of tomorrow who are going to improve the system and change the way it's implemented. So that's the second reason. Did I answer your question? Yeah, awesome. All right, so this is why there's a third reason, because it's fun to actually see how it's actually implemented. All right. Now you have a bit of control about the number of executors, the memory allocated per executor, and the number of cores per executor. In fact, it's control given to you over the command line, if you use the command line. So the command, if you want to submit an application to Spark containing all of your Python or Java codes that tell Spark what to do, it's called Spark Submit. So you invoke Spark Submit, and then you wait until it's done, and then it stops, it's done, and you have your result maybe stored somewhere on AGFS where you wanted them. Well, it turns out that there's a few parameters that you pass here. So the jar file is just your code. It's the Java code that you compiled. And this dash dash num executors is one of the hints that you give to Spark. In that case, you're requesting for Spark to create 42 executors, meaning containers in Yarn, on the cluster. Of course, it's only a wish because maybe there's not enough resources on the clusters. Maybe you only are going to get 30, right? If you want to know, there is actually a server somewhere called the Spark History Server. It's available, in fact, even if you run on your laptop, try localhost 4040. That's the secret address under which you find the Spark History Server. As long as your query is running, the server will be available. But if the query is done, then it's no longer available. So what people sometimes do is they put a sleep at the end of the program just to keep it alive for the duration of exploring what's going on. But basically, if you go to the Spark History Server, you can actually see a lot of information on what's going on, and you can actually check if there are actually 42 executors that were created, right? And if it's not the case, you just need to understand why. Maybe there's not enough CPU, there's not enough memory, and so on, right? Maybe you don't have enough machines in your cluster. But assuming it's available, you can request a number of executors like this, right? I think I have exactly 42 in there. All right. Something else? Oh, there's a question.
Why not use GPUs to run the calculations in parallel instead of multiple cores each running sequentially?
That is a very good question, and people are actually working on it. This is a very good question. It's in particular relevant for machine learning that you want to run stuff on GPUs. I think that some people did it, for example, for the pandas library in Python. They found a way of accelerating it. That's the beauty of data independence, right? We have the Spark API, but you can implement it in any way you want. And it would be absolutely possible to do it with GPUs. It might be people actually did it. We could actually maybe do some research and see if it's been done. But if it's not been done, it will be done. I'm pretty sure that there are people trying to do that. Right? Did it answer your question? All right. That's the beauty of data independence. You keep the API and you change the implementation without changing the behavior. Right. That's why tests are actually good. If you have tests in place. So what I tell all of my students when we build systems in projects, there is a paradigm called correctness first. Your first prototype should be correct. What it outputs should be correct. It doesn't matter if it's slow, you don't care. And once you're done with a correct implementation, then you optimize. And before you optimize, you use the correct implementation to generate tests. And then you can change the implementation, making sure that you still validate the tests. That's the way to go. So correctness first, and then you try to optimize. I think even Donald Knuth said it multiple times that if you optimize too eagerly, you're just wasting your time because you might not optimizing what is the actual bottleneck. So yes, that's the idea that you can then, when you have the test in place, swap the implementation without changing the behavior, and that is another kind of data independence. All right. So second parameter, so num executors. Another one is executor cores. And in that case, I'm requesting 2 cores for each executor, virtual cores. So if I do that, in total, this and this, how many cores do I need in total? $84, exactly. It's the multiplication, right? So you have 42 times the number of cores. It's important because it could have been that it's the total number, right? But it's really per executor here. And then you have the memory where you use these international prefixes. So you say 5G means 5 gigabytes, and it means per executor. And if you have 2 cores and 5 gigabytes, that gives you the size of your container in Yarn. It's requesting a Yarn container with 5 gigabytes and 2 cores, and we're going to have 2 slots in there, so 2 levels of parallelism in there that will share the 5 gigabytes. And of course, you can put it all together, and in that case, you need 84 cores on your cluster, and 42 times 3 is 126 gigabytes of memory. When in fact, it's a bit more than that. You do need a bit of air for the cluster to breathe. So technically, if you use, for example, 84 cores, it's a good idea to have at least, let's say, I don't know, to have 1 extra core that is available. It depends on the system. This keeps changing, right? Some people leave 1 core for each machine. They leave 1 core that they don't use to let the machine do other things with that extra core. it's a good idea, right? So for example, if you have 16 cores on your machine, you might do 3 times 5, that uses 15 cores, and the last core is left unused, right? Some people will do 4 by 4 and not leave an extra core. You just need to try things out and see how that works. The same for the memory. In that case, we would need 126 gigabytes of memory in total, but you need to make sure on every machine that there is a bit more, right? Because you still have an operating system to run, right? To support all of that. So you still need an extra core and a bit of extra memory. It's always a good idea. All right. So having said that, let's move on to this other kind of dependency that's called a wide dependency, also known as spaghetti, right? So this is when you have the group by, the order by, the join, the Cartesian product, distinct values, and so on, whenever you have this kind of pattern. And in fact, it corresponds to a shuffling in MapReduce, right? Remember the shuffle part? In MapReduce, there's only one. You map, you shuffle, you reduce. Well, in Spark, you're going to have to shuffle for every single spaghetti transformation, right? So it might be that in the same Spark job, you need to shuffle 5 times, right? Or 10 times within the same job. Of course, when you want to optimize, you try to minimize the number of shuffles. So if you can avoid some of them and have less shuffling, that's going to make your application faster. Going down to 0 is, for most of the use cases, not possible because it doesn't make sense, right? For most use cases, you do need the data to move a bit, right? To be able to aggregate it. So maybe you can get it down to 1 in the best cases, but not to 0. But we want to avoid too much shuffling. And you know why? It's because it's quadratic, right? You need every server to suddenly correspond to every server, a lot of data moving and so on. It also forces you to materialize the RDDs because you need to transport the data. So that's why you're forced to materialize. All right, so this creates a new stage, right? Every time you have shuffling because of a spaghetti transformation, a wide dependency transformation, you end a stage and you start a new stage after that. So in the general case, you're going to have, let's say, an RDD, then a narrow dependency that is compressed to the same stage. Then you have, let's say, a sort transformation. So you have to shuffle, and that's stage 2. And maybe right after the sort, you have, I don't know, a group by, which probably is a bad idea to do a group by after a sort, but let's say they did that. And then you shuffle again because of the group by, and then you are in stage 3. Now, what will typically happen on the Spark cluster is that the stages are sequential. So you typically will have the entire cluster going with stage 1, with using all the resources. Then you go for stage 2 again, the entire cluster, and then you go for stage 3, the entire cluster. That is a common case. I think the architecture is flexible enough that you could have several stages in parallel, like half of the cluster is one stage, the other half is another stage, and then maybe you join the 2 stages. I think the architecture will allow that, but maybe for your mental pattern, just think of it as sequential stages, which is always possible, right? There's something known as the Spark scheduler that I'm not familiar with this in details, but there are ways of scheduling what goes well. All right, so why did I say parallel stages? Because of something like this, because if you have transformations that take 2 RDDs in order to join it into one, as is happening here, then you see that the stages are not linear in that way, right? You have stage 1, stage 2, and then you join the output of the first stages, then you continue there, right? But again, what's typically done is you're gonna have stage 1 on the entire cluster, then it's done. You keep the intermediate results in memory or on disk, and then you do stage 2 on the entire cluster, keep the results, then you shuffle around because of the join, then you have stage 3 on the entire cluster, shuffle around, and then have stage 4, and in stage 4 there was non-spaghetti transformations. All right, for whom does that make sense? Right, so you see that they are sequential within the tasks, across the tasks on the same slot, and also across stages, if you keep it simple. All right, so this is what it looks like in general, and normally you should be able, if I gave you some code, some Spark code with transformations and actions that gives you a DAG, normally you should be able to draw something like that. And the way you do it is look for the spaghetti transformations and for the non-spaghetti one and try to redraw that, just figuring out where the shuffling is and where no shuffling is needed, and then you can squeeze them into a single stage, right? So this is on the high level how things work. And of course, at the end of stage 4, if you have an action, the materialized RDD will go right down to HDFS or to S3, or to your computer screen if it's small enough in that way. All right. For terminology, it's just a repetition of what I'm saying, but maybe to clarify a little bit. Typically, a stage is a vertical grouping of transformations that are non-spaghetti grouped as a stage. And then a stage can be split horizontally into tasks. This is the part that sometimes is confusing, right? You can consider a stage either as a sequence of transformation or as multiple tasks in parallel. And the trick is that in every task, you execute the underlying functions of the transformation without materializing what's in the middle. Yes, go ahead. Oh, yeah.
I have a question about the materialization. If I remember correctly, it uses the JVM bytecode or the Python dictionary on the underlying infrastructure. Is that not relatively inefficient as a format to encode the data with?
Mm-hmm. So the notion of materialization is basically orthogonal to the way you materialize, right? So generally, materializing just means that you actually store the data somewhere. It could be as a Python dictionary. It could be, maybe you materialize it as Parquet files on HDFS and so on. And technically, the exact structures that you are using are actually an implementation detail. This is an implementation detail. However, you just put your finger right on the next thing we're going to study, namely data frames, because you're absolutely correct that if you have an RDD with 1 trillion JSON objects that all look alike, this is the case where you should be using data frames, because the data frames will be able to store it much more efficiently. In particular, they will not repeat the keys of the JSON objects because the keys are in the schema. So this is absolutely correct that JSON objects are not the most efficient way to proceed. But even if you optimize and use, say, data frames, that's still considered a materialization. From the moment that there are actually the bits physically in the memory or in the disks of the entire RDD, then it is materialized. Right? Does it make sense? All right. And I'll come back on the data frames. This is coming up right after this. All right. So the stages. Either vertically a sequence of transformations with non-materialization of the intermediate RDDs, or horizontal splitting as multiple tasks, and the tasks are spread dynamically over the slots, the virtual cores. And a stage, a sequence of stages can be seen as a job. In that case, it's a sequence of 4 stages. Technically, if you have a DAG like this, so technically there's the DAG of RDDs, but technically, we also have a DAG of stages, right? It's also a DAG of stages. When we create a linear order of the nodes, in that case, it could be 1, 2, 3, 4, but it could also be 2, 1, 3, 4. This is called a linearization of the DAG, right? So a linearization of the DAG is a linear order of the nodes that is compatible with the arrows of the DAG. For whom is that clear? Yes, okay, a linearization of the DAG. Yeah, and there can be multiple linearizations of the same DAG.
Yeah, and in this case, if instead of the join, we would have a narrow dependency transformation, like I think union was an example, where we just append the stage 2 result to stage 1, and then that becomes stage 3. Would that still be separated in stages, or would we have one stage that forms everything?
So if you have a union, I think you can optimize more, because indeed the union does not require shuffling anything. So if you have a union, I guess you can just simply leave the data in place on the machines. You will probably still need to have the stages because you do need to compute the output of stage 1 and the output of stage 2, but you can start stage 3 without actually shuffling anything. And in that case, it's more efficient. And that really depends on the transformations. In fact, as I will have a slide later, imagine that you have insider information. Like it's not insider trading, it's insider querying. Imagine that I tell you, I give you the information that the output of stage 1 is partitioned in such a way that the values with the same key are always on the same machine. If I give you this secret information, then you do realize that the shuffling on the left is no longer needed, right? And that actually happens, and Spark is often smart enough to figure this out. An example of that is if you're sorting right after grouping on the same key, then the sorting doesn't require shuffling because the keys are already, because of the grouping, grouped together, right? So sometimes Spark is intelligent enough to figure out with the information that you can avoid some of the shufflings, right? Did it address your question?
Yeah, thank you.
Yeah, awesome. All right. And now about performance tuning, but this will not be new because thanks to your smart questions, we've already discussed that a little bit. Imagine that every time I trigger all of the computation and I call an action here and an action here. And what I told you is that you can pin, in the code, you can say, please pin this in memory or pin this on disk and so on. And then when you call the action, it only needs to compute that part. It doesn't need anymore that part of the data, right? So this is why pinning or persisting RDDs is useful. And again, you can do it at multiple levels in memory, on disk, both. Yes, go ahead.
Why don't we, in this wide dependency transformations, why don't we cache the result of a join? So it's an expensive operation, right? And we might be interested in that.
That's a good idea, right? After a join, it's a good idea to persist it.
Yes.
It might be, I don't know, it might depend on the versions, but it might be that the engineers figured it out as well, right? That they might prioritize the output of expensive operations as being higher probability of being persisted than the rest, right?
Thank you.
And the design is improved at every version, and every time it's based on what users do. Yeah, so that's a good point. All right, and here, that's basically what I told you as an answer to your questions, which was also a very smart question. If I do know that I need technically a shuffle, but I have insider knowledge of the fact that the data is already partitioned in a way compatible with my shuffle, then I just don't need to shuffle anymore. One way of doing that is pre-partitioning. If you ask specifically Spark to partition in a certain way, or maybe you output your data to HDFS already sorted in a certain way, that can help. Or if you've just grouped with the same key that you're about to order with, that's also a way of avoiding a shuffling. All right. And in that case, you might avoid some of the joins if you already made sure that it's pre-partitioned correctly, either explicitly or by using transformations. All right, that's it for the physical part of Spark. And now I'm going to address your question about the more efficient way of storing than JSON objects. And in fact, that's not new to you. I already told you that. I told you in the data modeling lecture that if you have a very large collection of JSON objects stored as JSON, one JSON object per line, and you can come up with a schema that satisfies some conditions, then you can and should copy over and store that file in a different format like Parquet, protocol buffers, and so on. It's going to take less space than JSON. It's going to be much faster to read and much faster to process. I already told you back then that this uses data frames. So think a data frame is basically a collection of valid JSON documents. A collection of valid JSON documents, if the schema satisfies some constraints, that's a data frame. You might remember the visuals, right? And it turns out that Spark is really, really good at data frames because data frame support was added. It wasn't there at the beginning of Spark, but then they added support for that. So let me tell you how that works in Spark. So an RDD is a collection of values, but that can be any value, even polymorphic. And then we have the transformations that have functions from a value to a value. The code might look like this, right? So I might have a text file, and then I apply a filter for the lines that contain Spark, and then I count, and so on, right? I reduce by key, and I take, that's my action, I take the top 10 results, right? Now, what if so this is text, right? So text is done like this. What if I have JSON? Well, the problem is, if I just use RDDs, Spark doesn't know and couldn't care less that it's JSON. It's just going to be text, and I have to take care of parsing it as JSON with my own code. So I have to actually use parse JSON. Me as a user have to actually write that in PySpark, parse JSON, then I create a Python dict when I have that, and then I use the Python way of looking up a key in a dict, but this is really Python code that I have to write as a user, and then I might map to in some other way and count. But you see that all the JSON part is extra Python code that I need to write. Spark doesn't know about it, right? It's all in the black box of the functions that I give to Spark. So in order to do it better, it starts with an observation. The observation that just like a relational table is a list of rows, or a set of rows, depending on the semantic, but let's take a list of rows. A data frame is also a list of rows, a list of records. The difference is that data frames might be nested, right? But a data frame is a list of rows. So you probably see now that if I create an RDD of rows, that technically gives me a data frame, right? A data frame is an RDD of rows physically. Who sees that? Right? A data frame is just a sequence of rows, right? So an RDD of rows emulates a data frame, kind of. Who sees it? I just want to see more raise hands to be sure. Okay. So in Java code, that would be the Java code, you would call it data set of row because it's more optimized than an RDD, but basically you can see it as an RDD of rows. But these rows must have the same schema. Otherwise, it doesn't work, right? You cannot create a data frame. So if the rows have the same schema, then technically, instead of looking at it as a sequence of records, a sequence of rows, I now view a data frame or a table if my data frame is flat, right? The nice thing about it is that if you do have an RDD of rows or a better structured data frame, then you can store it much more efficiently. And in fact, what's going to happen if you create a data frame like this, inside the memory of a single machine, Spark is no longer going to keep the rows row by row like this. Instead, it's going to group the data by columns. This is incredibly efficient. It's incredibly efficient. Why? Because in a data frame, the values in the same column have the same type. For example, if the type of that column is integer, then I just have integers here. And it's possible with languages like C++ or Java and so on. It's extremely efficient to store sequences of integers exactly. The thing is, what happens in memory is that the size, if it's 32-bit integers, you know exactly where to find them. If you have a sequence of integer and you need the 1000th one, you can directly jump there just with memory pointer calculations. Who sees that? Right? It's super efficient. I love to have the same type all over. And this is why we store it as columns. That's the first benefit, is we can highly compress, because then I no longer need to store the key, right? The key, I store it just once. That's the same key for all the records here. And then I only need to store the values. The second benefit is that, imagine that I have a data frame with 10 columns. But it turns out that my query only uses 2 of them. What can I do? I can ignore 8 of the columns. And if they are stored in memory separately, then ignoring the columns means I only need to read this and this. I only need to read 20% of the entire data. This is extremely efficient. I can just drop the columns that I'm not using. This is called projecting away, and this is an extremely important part of query optimization. Basically, the idea, when you have data flowing through your cluster, whenever you figure out that you don't need part of the data, then just get rid of it. And get rid of it as early as you can. Sometimes you can even get rid of it while reading the file. If the file is in Parquet and you already know that you only need 20% of it, you can already not even read the remaining 80%. This is extremely efficient because the bottleneck is reading the data from disk. So if we can just skip some of the reading, then we gain a lot of performance. For whom is that clear? Right? This is really fundamental. All right. So data frames take much less space in memory. First, because we can compress, and second, because we can easily drop part of the data we don't need. And when you use in Jupyter Notebook, you actually can write queries that look a bit similar, but this time it's not RDDs, it's data frames. This is not RDD, here it's DF. And the nice thing with a data frame is that you have this magic function SQL, and then you could put actual SQL in there, and that's going to actually execute on your data frame and give you another data frame. This is magic. And all of that is going to be converted to transformations automatically. All you need to do is type this high-level SQL. It's magic. This is absolutely powerful to be able to do something like that. So you see now why we've been brushing up on SQL in the first week, because it would come back, and now it's back. This is SQL. It's right there. And you can use it in Spark. It's called Spark SQL, but you will see it's technically almost the same language. All right, for whom is that clear? Right, so now I can go ahead and use SQL. So now, if I read data, Spark is very smart. For example, if I try to read CSV files, it's going to try to figure out the types. It might even automatically detect integers. You can also deactivate that and force a string instead, but this is what happens. If I have JSON, even if I don't even give any schema, Spark can actually try to detect a schema and infer one. For example, in that case, it might detect that foo is always an integer and bar is always a Boolean, and then it will build that data frame out of it, right? It's magic. Who doesn't like SQL? It's okay not to like SQL, I can imagine. Well, if you don't like SQL, that's fine, because you have an entire API for you that's called the Data Frames API. It looks similar to the RDD API. It's just need to be careful. It's not exactly the same methods, but you can basically assemble like this your queries with the dots. But again, this is a Lego game, right? It's the same as SQL. It's equivalent, just giving you more control. All right, now we have plenty of types available in data frames. The good news is I don't need to tell you much about it because we've pretty much covered it in the data models, right? It's the good old usual types that you already know. So I don't need to say much. I'm giving you that. I already gave it to you before. I think something equivalent. But there are always these correspondence tables. There are the JSONic types we've already seen with JSON, XML schema. There's the Python types, the Java types, and the data frame types that are over here, right? It's always the same ones. So again, that's very low effort for you to actually learn this. All right? The same goes, so those are the atomic types, but the same goes for the structured types. There is an array type and a struct type. These are the most important ones. The array type in a data frame corresponds to a JSON array. The struct type corresponds to a JSON object. And there is an extra type called the map type, which is a bit different. It's a little bit like an object, except that all of the values have the same type, and the keys can be something else than a string, right? So this one is a bit special, right? It's used a bit more rarely. It's really the array type and the struct types, so that corresponds to arrays and objects that you're probably going to be using a lot. All right, so it's magic. You can read data frames out of JSON if it's sufficiently structured, out of Parquet, CSV, text, out of a relational database if you want to use the JDBC connector, out of PostgreSQL, Avro, and there are so many formats I cannot even list them. They keep being invented, and every time they connect them to Spark in a way you can open them, and you can read from this format and you can write back to these formats, right? So I encourage you to use them. If you have a schema, do not use JSON. It's a very smart remark. Do not use JSON. Try using Parquet, Avro, whatever format is more compact and like data frames. This I'm only telling you it's a feature that is used a bit less. If you want, you can actually create a schema in the form of a Java class or a Python class, and then use it instead of raw. It's basically just a way, it's really a mapping from a schema to object-oriented programming. This is really what it is. If it doesn't make sense to you, then don't worry, right? But for those of you who are interested in this, in mapping object-oriented programming to databases, then you can also use a more specific class than the generic raw class. Okay, so that's it. That's why the SQL brush up was useful. And for those of you who prefer, you have this. At the exam, you can use either or. I really don't mind. You will have both anyway. My personal preference is Spark SQL. I find it easier, but you can do this. And there will be at the exam some of the problem solving where we ask you to work on data frames and write Spark SQL or the data frame API. Okay, and all of that is magic because when you use data frames, behind the scenes it's going to be RDDs, but Spark is doing it automatically for you. You don't have to worry about this, right? So this is Catalyst that's taken from the paper. That's the optimizer, because from the moment you use data frames, you can optimize a lot of things. And this is going to be super fast, right? So I'm going to stop here. I think that some people are eagerly waiting to take an exam right after us. So maybe we can help them by letting them the room. And you get your 5 minutes back. Thank you very much for attending today. I'll see you tomorrow at 9 a.m. in order to continue this lecture. Thank you very much.